video at some point. I'll try to get that back. All right. So this is a flip lecture. So what I like to do is, I don't think, talking about concepts online is the right way to go, but I plan to do more like a mini lecture, sort of mini concept cover throughout. So this means I won't go into details. You need to watch videos or read the book to get more details about these concepts. And so my goal is that most of the things that I plan to discuss are going to be on going to be more questions, like more targeted towards assignments or problem sets or things of that nature, and midterms, that sort of thing. And from time to time, I won't be able to answer all your questions on the chat here, but I will try to pause and give you some time to think about some questions that I will give to you, and then you can, while you're doing that, I'll try to pick some questions to answer. All right. If you have any comments, please don't speak. Just type into the chat. Okay, exam 2, all of those things we will discuss at some point. I think the main thing is that I don't think we have a date yet. We are discussing that. But I think you're going to see that on the Sakai announcement. So just keep checking Sakai to make sure that you know when the date is. Now, all these exams are take home, so they are offline. That means you can download it and print it out and do it and then upload it or whatever. The instructions will be given to you. So even if you, they are not online, so in other words, even if you lose your connection, it's still going to be okay. All right. Any other questions I can answer quickly? Okay, great. Okay, let's move on. So these are our learning goals. So some learning goals. I want you to understand we are discussing hashing. That's our last topic. And be able to describe the properties of hash tables and applications. So the reason I'm giving you learning objects, just like in 111, you should think about these things and ask the question, do I know how to do these things? Because these learning goals are really, really important because they map directly into the exams and assignments and problem sets and all of those things. Okay, and then we're going to learn something new today called priority queues or heaps, and we'll talk about that concept. Okay, this file that I'm using is in Sakai, so if you like to get a copy of this file and start annotating yourself, that's fine too. So you're welcome to do that. Okay, so let's go back and think about hashing one more time here. Okay, so the main thing about hashing is sometimes this is such a simple idea, but it can be confusing. So I want to kind of make sure that you get this idea. It's very, very simple, but it can also be more difficult to understand. So you're given a key, and what you're going to do is you're going to send this key to what's called a hash function. And this hash function has to be chosen very carefully. And hash function gives you what's called a hash code. And then this hash code goes through a filter. What that filter does is to take this hash code and modular that with the size of the table. So we might assume that this table is of size M. So we have a table of size M. So we're going to take the hash code, because hash code could be something larger than M. So if it's something larger than M, it's going to go into whatever the place. Once you mod something, then you're going to get the right place, and that's where this hash code is going to go. So that's the understanding of how the hashing works. So this is a very key point in hashing, that there's a hash function h, and then the hash code creates a hash code, and the hash code get modular with the table size M, and so it goes into this. Okay. So one thing we expect from hash table is that the insert and search has to be big O of 1. It's constant time. It seems like a random kind of a table, but somehow because of the hash function, it tells us where this key is going to be. All right. And so the load factor of a hash table is going to be the number of keys divided by the size of the table. So if you have a hash table like this, let's say we have only 3 slots, and then we have a bunch of keys in the hash table. It's a separate chaining hash table. And in this case, the load factor is going to be the number of keys, which is 4. There are 4 keys here, divided by the size of the table, which is 3. So it turns out to be 1.33. So that kind of gives you an idea about the average length. This is like the average length of a chain. Okay, and so let's ask some questions from you. You can type in some answers to these things. What determines the performance of a hash table? Okay, load factor, big O of 1. I think I'm asking for factors that what determines. Does the load factor really determine the performance of a hash table? Okay, there are more answers coming in. Number of nodes in the same index, that looks good. The uniqueness of the hash function, that looks good. Okay, great. So I think I will accept these answers, that the number of nodes. So I think what determines is going to be, I say, number of nodes in a chain. I apologize for this thing, it keeps coming. Chain. And also the hash function. So that's true. The uniqueness of the hash function is very important. And also collision resolution. I think all of those are good things. But basically what you like to do is to keep the performance well, you have to keep these chain lengths smaller or shorter. Okay, next question. Is the load factor a good indicator of the hash table performance? Do you want to type in some answers to that? If you just think about the load factor alone, could that be a good indicator of the hash table performance? Okay, so most people tend to think yes. We're looking for, looks like we're all agreeing with each other. Okay. Okay. I think, I think that would be a good idea to do a poll, but let me just, okay. But I think the answer is no. You could have, for example, if you take a hash table like this,
Okay, S.
okay, hopefully I'm back. I have to reshare my screen. Okay, clearly the performance is not as good as I thought it would be. Okay, can you see my slides and can you hear me? Okay, great, thank you. So the last thing I left was that I asked the question, is the load factor a good indicator of the hash table performance? The answer is may not be always yes. So for example, this hash table of 1, which seems like a nice good load factor, that seems to indicate that the average length of a chain is 1. But if you look at this, it's not the case. So what determines this performance? What causes this kind of behavior in a hash table? Just a few answers. Right, number of collisions is a good one. A bad hash function. That's what I was looking for. So if you have a good hash function, and that's the most important thing for getting a good hash function. Okay, now I'm going to give you an exercise to think about. Okay, we have 10,000 strings, and each one is length 5. And the strings are from the alphabet. Let's assume that we have these 26 characters A through Z. And we have a table of size 10,000. So if you have a perfect hash function, we might be able to map each of those things into just one chain length is going to be 1. Okay, and we're going to be using the hash function that h of a string is the sum of the characters. So the question I'm asking is, what is the average length of a chain in this situation? I will draw this, but I'll let you guys think about how to answer this question. So let's take a table of size 10,000. And we have 10,000 keys, and the hash function is that given a string with 5 characters, each string has 5 characters, and the hash code is given by the sum of the characters. I have to disable this thing next time, but let me just S4 plus S5. Okay. So the question we're asking is that if we use this hash function, what would be the average time? So someone said 80. That's good. Let's see how we get that. I think one of the things you can think about is that, given a string, let's say that we assign some numbers for A, B, C. So let's say A is 0, B is 1, and Z is going to be 25. Now this is similar to getting numbers from the ASCII table. Okay, so given that, you have to think about, for each string of length 5, what would be the highest value and what's the lowest value? What's the upper bound? What's the lower bound? Given this hash function. All right, I see 0 to 125, which is correct. In fact, the lower bound is 0 because you can imagine that that would be the string AAA 5 times. The upper bound, the highest value will come from 5, 5, 5, 5 times. 25 5 times. That's going to be 125. All right, so I'm glad to see you're getting that. Now, what that means is that because this hash code always falls between 0 and 125, we're only going to use 126 locations in the hash table to build things. All right, so 126 locations will be used to place these chains. So we're going to place these chains in the 126 location, but we got to put 10,000 keys in 126 locations. And that turns out to be roughly 80. If you divide 10,000 by 125, you get about 80. Any questions? Okay, so the average length of a chain is 80 for this. Now we're asking the question, given this fact, is the insert and search still big O of 1? Okay, insert would be big O of 1 because we are always inserting to the beginning of a chain. But the search is not going to be big O of 1 because when you search, you're going to be searching in a chain that is of length n over 126 of a chain. And so the search requires this complexity. And because we drop the constant, this is actually big O of n. So in other words, when we have a bad hash function, it turns out that this is going to be linear, although it's a very small number because if n is large, this is going to show up. But right now n is 10,000, so it's not too bad. It's still 80 n over 126. Okay, you guys still hear me? Okay, so the transition between big O of n over 126. So that's because we have a very fixed number here. So the chain length turned out to be n divided by 126. So it's really a function of n, the length of the chain. So the length of the chain, this is the length of the chain. So that's going to be the performance, because if you're going to be searching, you have to find it. Okay, so, and because 126, we can forget about 126 in the big O discussion, we have big O of n. So this was caused by the function that is a bad function. Okay, so because it's a bad function, it's going to have many collisions. Okay, so the next idea is what we call rehashing. So in fact, we could have, going back to this, saying if we realize that these chains are getting too long, because if the chains are too long, then your hash table is no good. So you have to make the chain length manageable. So what one can do is to define a threshold. You can say the chain cannot be more than 3. If the chain becomes more than 3, then you have to resize the table and rehash all the keys. Okay, so what does that mean? So for example, let's say that we have, let's take a small table here. So we have, let's suppose we have a hash table of size 2. And that has only 2 elements here. So let's assume that we have a key A, which has the code, let's assume that this is going to be code 4. Key B has the hash 10, and key C has the hash code, let's assume this is going to be 50. And key D has the hash code 40. All right, now you might understand why the 4, 10, 50, 40 went into the location 0. Can someone type in why I put those hash codes into location 0? Very good. They are even. Because when you take the mod of those things, they become 0. And let's suppose now I have another key, E, which has a hash code 3. So that goes into the odd location. All right. So because now one of the chains exceeded our threshold, chain has become length 4, what we need to do is to rehash this table. So typical process for rehashing is that you double the size of the table. You double the size of the table. Okay, now I want you to take a little bit of time, think about this, and write on a piece of paper where these keys are supposed to go. Now we have a new table, so you have to rehash these keys, A, B, C, D, E. Where do they go now? So try doing that. All right. It shouldn't take too long, but let's see if you got this. So A, now I think your table size is now 4. So therefore, you have to mod every hash code with the table size 4. So if you take A still go into location 0 because 4 mod 4 is 0. The B, which has a hash code 10, goes into location 2 because 10 mod 2, 10 mod 4 is 2. And C, which has a location hash code 50, if you take 50 mod 4, that is also 2. So I'm going to put the C in front of this one. It's going to be 10. So notice that I always put things in the front. And then the D, which has a 40, goes into location 0. So I will put that in the beginning. So this was A and 4. And then E, which has 3, that goes into 3 because 3 mod 4 would be 3. So notice that you got a better distribution now, and now it's under the threshold. Now, the key thing here you have to know is that if you store your hash code with your keys, you don't have to recompute the hash code. You just have to take the mod. And so that's going to make it more efficient. Okay, I'm going to give you another problem to think about here. So suppose you insert 10,000 keys into a hash table with an initial array size. I'm just going to make this a little bit faster. So let's make it 50. So suppose you insert 10,000 keys into a hash table with an initial array size of 50. The hash table is required to maintain a load factor of 3. Assume that keys are evenly distributed based on the hash function. So we know that max length of any chain is going to be less than or equal to 3. All keys have some integer code that is computed using a hash function. Let's assume that the inserting keys takes unit time. We know that's the case because we always insert to the beginning of the chain. Okay, so there was a little question coming up, so I will bring this back while you guys are thinking about this. So let me answer your questions while the others are working on this problem. Okay, so one question is, why did you put C before B? That's because C came after B. So the new guys always go to the front. All right, someone already has an answer to the question here, 29,050. All right, so let's give a little bit of time. We do always double the size. And you'll have to think about that in this problem too. Okay, so let's start moving here. So our goal is to insert 10,000 keys into a hash table of initial size 50. So initially we have, let me put it this way here. So this is, say, the table size is initially 50. And how many keys can we insert into this hash table, assuming we have an equal distribution? So because we are allowed to go up to a load factor of 3, that means we can insert 150 keys. And so the number of operations that is required to put 150 keys is 150, because each one takes constant time. And once you do that, your table is full, because 50 now has 150 keys. So that's a load factor of 3. Next, you have to double that size. When you double the size, you're going to be able to put 300 keys into that. Now, in fact, you're not going to put 300 new keys, because 150 of them will come from the old table. So you're actually putting only 150 new keys, and you can put now 300 keys. So because each one takes constant time, it will take 300 operations. Next, you're going to double the size, that's 200. Now, you will have to copy these 300 keys first, and then you can put another 400 keys to make 600 keys. All right, so now you have 600 keys, and that requires 600 operations. So similarly, we can just go, this becomes 400, this becomes 1200, and this becomes 1200, then 800, 1600, and 1600. And then it becomes 1600. Oh, wait, I made a mistake here. It's not 1600. It's going to be 2400. So we can do 3 times as much. And the table size becomes 1600. Now I can do 3 times that. That's 4800 keys. And then I can double the size. That's good. This gives me 9400. 93 times that, so 96. Okay, and I'm still not done, because I still have 400 keys left, because I have to go to 10,000. So I'll have to double this size. That goes to 6,400. Then I can put 3 times as much. So 64, 128 plus 64 is 180. Is that 196, 120, 128 plus 64, right? So that's going to be 192. So in fact, I only have 10,000 keys. 10,000 keys, so I can only go to max of 10,000. So that means I don't have to, although I have a lot of space here, right? Because I have a space that I can use. That much space is left. Okay. So, but I'm only using 10,000. So what's the, how long does it take to insert all 10,000 keys? It's going to be the sum of these guys. Did anyone compute that number? Oh, wait. No, that should be 10,000, not 90,000. Okay, so someone computed it. I haven't checked this, but someone claimed this to be 29,050. Very good. Okay. All right. Do you have any questions before we move on to the next one? Okay. I have a few things that I want to note that when you want to use Java API for hash table implementation, you have two things that you can use from Java. That one is called hash set, which is in fact part of the collection interface from Java. So it's right here. Okay, and it implements the set interface if you understand implementation things, but it's not really important to understand. But the hash set idea is that you don't need keys and values, so you can just put keys into a table. So if you have a bunch of things, you just want to store them, you can use a hash set. And there are a bunch of methods that you can look at, things that are useful. And also, the other thing is the hash map. But the hash map idea is that you can have a key pairs that can be mapped onto a hash map. So if you have keys and values, then you can map them into a hash map. So for example, you might think that you want to store your net IDs with an array list of integers. Excuse me, those are your values. But that could be just a set of courses you're taking. You're taking a bunch of courses. So for each net ID, you can then map into a set of courses. So that's a great way to store the relation between map and a net ID and that. Okay. And you can find some code examples in my folder if you like to take a look at those. Okay, I want to start the next concept here. Okay, our next concept is called a priority queue. Now, we're all familiar with this concept. It's called FIFO, right? What does that mean? First in, first out. Very good. Okay. So those keys are first in, first out. So imagine, in fact, before that, if you search Andiguna priority queues, you will find one of my YouTube videos. When you have time, you can watch it. But it's not in Java, so just understand the concept through that. Okay. So let's take a motivation for using a priority queue. Suppose we want to model people who come into a grocery store. So the first person takes 20 minutes for the groceries. Second one takes 2, third one takes 10, and fourth one takes 5 minutes. If you put them in a first in, first out queue, you're going to be serving 20, then 2, then 10, then 5. So let's compute the average wait time for all the people in this queue, assuming that no one else comes in to this queue. Now, here's how I'm going to compute that. The first person will need 20 minutes to be served. But the second person need 20 plus 2 minutes to be served. Because the second person has to wait 20 minutes until the first person is saved. And then the third person must wait 22 minutes, which is that, plus 10 more minutes to be served. And the fourth person must wait 32 minutes plus 5 more minutes to be served. So basically, the total time required to serve all 4 people in this case is going to be 20 plus 22 plus 32, 37. All right, and if you add them up, you're going to get 9, 11, 1, 6, 7, plus 4 is 11. I think it's 111. So if you want to think about the average time, you divide that by 4. All right, so again, there's a question about why it's not 20 plus 2 plus 10 plus 5. That's because the second person must wait until the first person is served. Okay, so hopefully I did my math right. So the average wait time for 4 people is going to be this, and that's going to give you 28, 30, going to be 7, it's 28, and 31 maybe, yeah, it's about, I don't know, 7, something like that, right? Roughly 27 minutes. So let's just say roughly 27. Okay, now, just 27.75, right? Okay, so here's my question. Now, we serve the people on a priority, on a first in, first out queue. What if we change the order we serve people? How would we serve these people so that average time for everyone is going to be lowered? Do you have any suggestions about how I should serve these 4 people? Okay, so someone said lowest to the highest. Let's try. All right, so if we're going to do lowest to the highest, you can give it a try. For some reason, my tablet. Okay, so if I'm going to serve the lowest, it would be 2 here. The next one is going to be 5. Next one is going to be 10. Next is going to be 20. All right, so if we compute the average time now, the first one needs 2. The second one needs to wait 7. The third one needs to wait 17. That is 7 plus 10. Fourth one needs to wait 37. That's 17 plus 20. Then you take that sum, divide by 4. Okay, so the average now is going to be, the sum of this is that's 54, 61, 63 divided by 4. And that's about 15 minutes. So now, this is the idea of a priority queue. So the goal here is that to maximize the overall performance of the system. So without giving first in, first out doesn't really work very well here. And if you do like a priority queue, so for example, you might say in the grocery store, people say, okay, people with the lowest amount of food will come forward, and you just serve them. If you do that, you serve everyone better. Now, this is not just going to apply for grocery stores. Now, imagine that you're streaming movies, and you might want to stream the smaller movie first rather than the larger one, because otherwise, if you're in a queue, the larger ones have to, the smaller ones have to wait a long time before the larger ones are done. Now, this idea of a priority queue is quite important and quite useful, a very good idea in computer science. Okay, so the properties of the priority queues are that you can add items and you can remove items. In other words, someone should be able to join this queue anytime, and also we always remove, but we always remove the one with the let's say the highest or the lowest. In this case, I say lowest, but it doesn't matter. You could do whatever you want. So you can have a max priority queue or minimum priority queue, and so you could do anything you want there. Now, the important thing is that you need to efficiently support an insert and remove and looking up. In other words, in this case, I'm saying most, but you can say least. It doesn't matter. I think let's say most. So we define most by saying the person with the smallest amount of groceries is the most prioritized person in this case. So when you're trying to implement a priority queue, so the question is now, how would you implement something like this, like a data structure that has these properties? You want to be able to efficiently insert something, remove something, and peek, or you want to be able to look at it. So one of the things, I'll start filling this out table, but let's suppose that we use a random array to do this. Random array to insert, implement a priority queue. So inserting to a random array is, we know we just put it anywhere. It doesn't matter because it's random. But finding the max would be what? If you have a random array, the finding the max would cost you, finding max or min, it doesn't matter again, would cost you big O of n because it's random array. So you have to look for it. And if you have a sorted array, what is the cost of insertion? The cost of insertion is big O of n because we have to make sure we maintain the sorted property. But finding the max is easy because we know if it's sorted, it's going to be the beginning or the end of the array. So it's really easy to find that. Suppose we have a BST, not balance. Inserting could be as bad as big O of n because you might have a very bad tree. And finding a max means you have to go all the way to the right to find the max. That also could be big O of n if the tree shape is not good. Can someone type in the insert and find max for AVL trees? Okay, log n. That is true. AVL tree is a balanced tree, so we could insert time. Insert in log n time. Because we can find the max. Find max would be the, in a AVL tree, the max would be the rightmost element in a binary search tree, right? So this would be the max. And this is the minimum. Because the BST, if it's a BST or if it's a AVL tree, we know that the max and min is the leftmost and the max is the rightmost. So you could do it in log n for both. Now we are looking for some other way to think about this. Okay, I didn't put the peak here, so let's worry about that later. That's okay. So we need another data structure. In fact, this is where we are going to define a data structure called a heap. So in the heap data structure, we should be able to do, we are striving to do insert in log n time. but we're going to find max and in big O of 1, finding the max, which is more like peak. But if you remove max, so that means suppose we remove the max, we can do that in log n time. All right, so we have a very good data structure. This data structure is really well behaved. Both insert, find max, and remove all work really well. Okay, now how can we do this? So our goal is to design new data structure support insert, find min, and also remove min. Notice that I interchange. I use, sometimes I say remove min, sometimes I say remove max. It doesn't matter, because we can work with either max or min priority queue. They can be only one type, depending on the applications that you can do that. So let's go to the next slide here. Okay. Yeah, let me ask you a question here. Okay, my question is this. What algorithm we discussed recently can be efficiently implemented using a priority queue? I'm going to call it PQ from now on. Do you want to answer that question? What algorithm we discussed recently can be efficiently implemented using a priority queue? That is true, the Huffman coding. Okay, remember Huffman coding, that we have to find the two minimum things always? So in Huffman coding, we have to always find the two minimum things. Or Huffman tree. When you're building the Huffman tree, in fact, that's exactly what people use to build the Huffman tree. Because if you recall Huffman tree, you have to find the, two minimum things, and then you put them into a tree. Excuse me. So you have to be able to do this efficiently. And because we mentioned that efficiently means that log n time for both finding the two minimums and putting them into the Huffman tree. Now, the data structure that's going to implement a priority queue is called a heap. And these heaps have two invariants. One is called shape invariant. Shape invariant means that heap is implemented as a binary tree, not a BST, but a binary tree. What we mean by a binary tree is that it looks like this. In fact, not only a binary tree, heap is actually implemented as what we call a complete binary tree. So the definition of a complete binary tree is that all levels are full except the last level, where you go from left to right. Go from left to right. Why do we care about this? The main reason is that we like to find a good data structure to implement a heap. So in fact, if you think about something like an array, let's take an array, and we don't use the first element of the array, but we put some structure like this. starting with 1, 2, 3, say 5 and 6. And let's suppose that we put some numbers here. Let's say this is 30, this would be 50, this is going to be 60 and 65, and this is going to be about 100. Okay, let's suppose I do that. Now, in fact, without saying it explicitly, I actually defined a tree. What is this tree? The tree goes like this. The root of this tree is 20, and the left child of this tree is 30. The right child of that is 50. So the definition would be that given the ith element of this array, the left child is given by a of 2i, and the right child is given by a of 2i plus 1. All right, so why is it important? Because if you take one index 1, the left child is 1 times 2, 2 times I. Right child is 2i plus 2. So that's going to be 3. So who is the left child of 30? Can you type it in? 100, left child of 30. Someone said 60, okay. All right, so the left child, if you want to compute the left child of 30, you look at the index of 30, that's 2. You multiply that by 2, that's 4, so the index, that is 60. And the right child of, that's going to be 5, where the element at the 5th location, which is 65. And the left child of 3 is going to be the one with the index 6, that's 2 times 3, and that gives you 100. Now what you see is that this is called a complete tree. So the nice thing about this structure is that it's compact. Every element, the array has no holes, because you can always use an array to build a tree. So this actually, if you think about this, you can build any tree without any pointers using an array. All you have to do is you say, I don't use the 0, 1, but you're going to say, if the root is as of I, then the node, if the node is as of I, then the left child is as of 2i, right child is as of 2i plus 1. So you can use an array to implement a tree. And so it's a great thing because you don't have to worry about pointers and have a lot of overhead on that. Okay, so that's the shape invariant. The order invariant says that for each node, the value stored in the node is less than or equal to the child nodes. So using that, if you look at this, I intentionally made so that the parent is less than or equal to its children. If you take 30, it's less than or equal to 60 and 65. Okay. All right, so that's the order invariant. So the main thing is that during insertions and deletions, heap must maintain variant and order invariant. That means you have to make sure that it doesn't break. In fact, a lot of people write very good assertions to make sure that's the case, because if you break your heap, it could have very bad performance for your priority queue. Okay, in fact, we just answered this question. So this is the Huffman tree. Okay, now take a little bit of time to determine which ones are heaps and which ones are not. I'm talking about min heaps. So think about the shape invariant and order invariant. Okay, first one is not a heap. What about the second one? Yeah, try to see if you can make the first one a heap by moving around things. Okay, second one is. Third one is not a heap. Okay. Okay, very good. So first one is not a heap because this element is bigger than that, right? And because it's a min heap, you must have the parent always less than or equal to the children. The second one seems to be fine because every node, the parent is less than or equal to the children. Okay, that seems right. Okay. And the third one, did anyone say anything about the third? Okay, third one is not a heap either. Let's see why that's the case. Are you sure third one is not a heap? Is third one, I think third one is a heap too, right? Why is it not a heap? Right subtree does not have an equal amount of. Oh, that's correct. Yeah, you're right. So it is not a heap because this element could not be here. It has to be. Well, actually, no, it's fine. It's fine. I'm sorry. No, it is a heap. Correct? Because every level is full. This level is full. And then the other level go from left to right. So third one is, okay, so someone said second one is not a heap. I think heap, this is no. This one is yes. Okay, so I'll give you a little bit of time to think about this, but if you have a lot of disagreement, let me know. Okay, first one is no because these are in the wrong order. Okay, let's see if we can fix this first one to be a heap. Okay, if you're going to fix the first one to be a heap, the heap means that the parent is always less than or equal to the children. All right, so what we're going to do is we're going to do this from the bottom up. So we look at this part. Is that a heap? That's true. So because 11, and I want to get this color here, 1 second. Keep coming back. All right, so see, this part is okay. And all we have to do is now, if we exchange 11 and 41, that's going to be okay, right? So if you look at this now, the right-hand side of this tree is a heap because everyone is, parent is always less than equal, parent is less than equal to the children. If you look at these guys, this one is okay. And if I switch these two, then now it's a heap on that side. But I got to fix this one because then I will switch these two. It's not the right way to do it, but I'll make it a heap. by doing random things anyway. So now it's a heap. Now the second one is a heap once I do these swappings. All right. Okay. I will keep. I have you. I understand your things, right? So okay. So what I like to do is now the next few minutes, I want to kind of show you how to build a heap. So the first one is insertion operation in a heap. So let's say we have a bunch of random elements come in. 14, they can be equal, that's all right. 36, okay. So what I'm going to do is I'm going to show you how we build a heap. The way we build a heap is essentially you get the first element, so that goes into as the root. And then you get the second element, you insert that second element to the next place, but because now they are not in the right order, because 15 is supposed to be less than 32, so you would swap these two guys to get 15 and 32. And then you get a 16 element, and 16 element goes to the next available location, and it maintains the heap order property. All right, so this is still a heap because the root is less than or equal to the children. The 14 comes in, so the 14 usually goes here because it goes to the next available location in the array. And if you think about this, the array, this one has index 1, this one has index 2, this one has index 3, and this has index 4. That's the index of the array. So 14 goes there, but the problem is 14 is not in the right place because 14 is less than. So what we're going to do is we're going to just swap those two, 14 and 32, but 14 is still not in the right place. So we would swap 14 and 15, and we get a new heap now. So this is how the heap looks like once 14 is inserted. All right. So notice that it maintained the heap order property. It's a complete tree. And also the parent is less than or equal to the children. So then comes 30. 30 goes here. Nothing needs to be done because 30 is less than 15. And then comes 36. 36 goes here. Nothing needs to be done because 36 is less than 60. And so here is the heap built from those elements. Okay. So the basic idea of building the heap is that you always insert to the end. So I'll give you like maybe a quick one here, quick exercise. Okay. All right. So here's an exercise for you to do. Build a heap with 2, 3, 6. Those are the keys. I want you to build a min heap. Let's take 2 minutes to do it. What was the question there? 36 on the left subtree, or do you need to place it on the right? No, 36, always the new elements go to the next available location. There's another one comes, it'll go here. It's always the case. You're filling from all levels and then go from left to right. All right, someone did that. So in fact, this is the easiest one because I put the 2, 3 comes in, then the 4 comes in, then the 5 comes in, 6 and 7. And I don't really have to do anything, right? Because it's already in that order. How about if you build a max heap? So the max heap is that, let's do that as sort of the last one, because that's more challenging. So the max heap means that my property, the heap order property, is going to be children are greater than or equal to. So max heap child is greater than or equal to the left heap order property for max heap. All right. So if you build a max heap, let's see what happens. Now this one was you could just insert them in n time, right? In fact, this costs us only big O of n operations to do it. But now, if you're doing a max heap, it's going to cost you a lot more. So let's see how it works. So the 2 comes in, you're good. And then the 3 comes in, you're not good. So you have to swap those 2 because the big one has to be on the top. And then comes 4. 4 is okay because, well, it's not okay actually. 4 comes and it has to swap those 2. 4 and 3. So now we have this heap 4, 2, 3 right at the moment, and then 5 comes in. So the 5 typically goes here, but the 5 has to be swapped. That's why it's called sift up. And to get this into the right place, so 5 and 2 get swapped, and then you swap 5 and 4. So eventually it'll look like this. Okay, now the 6 comes in. What happened to my 3 here? Okay, oops. It's going with the scroll. All right, so now the 6 comes in. So the 6 is going to go here, but the 6 has to go up. So in other words, 6 will end up at the top, and the 5 will end up here, and the 4 end up here and here. All right, now the 7 comes in. So we have 6, 5, 3, 2, 4. So when the 7 comes in, I'm going to put the 7 here, but 7 has to be taken upstairs. That means 7 will go here, 6 here, 3 here, 5, 2. All right, so we build a max heap. So that is a max heap. And I think you need to try more problems. There are some problems in the videos, and I might send you more problems. So you need to understand the heap properties and also how to build a heap. using a bunch of keys. Now, notice that in the Huffman coding case, we would build a heap, and then it would build a min heap, and then we'll take the two minimum things out, and then we keep doing it until we are done with all of those things. Okay, 2 minutes left. I will let you ask any questions. How was my day? Is that a question for me? Or yeah, thank you. It was good. How do you think this worked out for you? Is this okay? Okay, great. I'm glad you are happy with it. Okay. Good feedback. The online test, I think it's going to be, it's not an online test. It's really an offline test. You will be given the test, you do it offline, and then you upload it. How is Newtown in this amazing time of year? Newtown is a little town close to Trenton. It's a great place. It's very, I wouldn't say rural, but a lot of farm things are here in Newtown. All right. Do we need to know how to implement a heap? Yes, I think it's important for you to kind of, in fact, the heap implementation is just implementing two operations, insert and delete. Those are the only things. And usually you implement a heap with a simple array, like we discussed. Test look like an assignment. Newtown has no corona, that's true. I don't know, but Bucks County, where I live, I think Philadelphia has a lot of corona cases. Topics for the next midterm, I'll try to find out for the next lecture. All right. I'm happy to stay here a couple more minutes. It's 8 o'clock. You're welcome to leave. Thank you for coming. I kind of like this chat because I never get this much comments from you during class. It's kind of great that you're expressing yourself here. Is stacks and queues? Probably not. Again, I will have to confirm that because we don't have the exam yet. All right, so it looks like people are slowly leaving, and it's probably time for me to